Welcome back to the basic concepts of real function theory. In my previous lecture, I have given the properties of convergence of sequence of functions. We dealt with two types of convergences. One is pointwise convergence of sequence of functions, and also uniform convergence of sequence of functions. And further in the proof of existence and uniqueness theorem, we deal with a series of real functions. Now we will discuss a uniform convergence of series of real functions. So consider the infinite series summation n goes from 1 to infinity unx. So an infinite series of real functions uns, each of which is defined on some real interval, say AB. Now to talk about the convergence of the series, we first form a sequence of partial sums of the series. So consider the sequence of partial sum. So consider the sequence of partial sums of the series call it F1 is U1, F2 is sum of U1 and U2, and so on. Fn is U1 plus U2 plus etc. plus Un. So that is summation I goes from 1 to n ui. Now we define definition so let this be definition 1. The infinite series summation un n goes from 1 to infinity is said to converge uniformly to a function say f on AB if it's a sequence of partial sums which we denoted by Fn converges uniformly to f on the interval a b. Now, to make sure that an infinite series converges uniformly to a function f, we have the following theorem, which is known as a Weierstrass M test. So, theorem Weierstrass M test so let Mn be a sequence of positive constants, be a sequence of positive constants such that the series of these positive constants Mn, n goes from 1 to infinity, converges to some number. Now, let the series of functions un, n goes from 1 to infinity, be a series of functions such that the absolute value of ux is less than or equal to absolute value of unx is less than or equal to mn for all x in the interval a b and for all n is equal to 1, 2, 3, etc. Then the conclusion is, then Weierstrass M test says, then the series of functions, then the series un, n goes from 1 to infinity, converges uniformly on the interval a b. So, each term of the series is bounded by a constant, and if the series formed by that constant is a convergent series, then the series of functions converges uniformly on the interval a b. So, that is a test. We will see an example verifying this fact. So, example, say example 1. So, consider a series that is summation n goes from 1 to infinity sin nx divided by n square, and this is defined on the interval 0 less than or equal to x less than or equal to 1. So, now the sequence of numbers mn which is 1 by n square the sequence of numbers is convergent. So, we know that summation 1 by n square, n goes from 1 to infinity, is a convergent series. So, if you consider unx, which is by definition sin nx divided by n square, and so therefore, if I take the absolute value of this is less than or equal to 1 by n square, as sin nx is less than or equal to 1, is bounded by 1 on the interval 0 to 1. And this is also true for n is equal to 1, 2, 3, etc. So, therefore, by applying Weierstrass M test, with the mn is equal to 1 by n square, and mn n goes from 1 to infinity is finite. We conclude that the series of function sin nx divided by n square for n goes from 1 to infinity, the series of function converges uniformly on the given interval 0, 1. Now, another important tool which we will be using in the existence and uniqueness theorem is Arcela-Ascoli theorem. Arcela-Ascoli theorem says that if you have a sequence of functions which are uniformly bounded and equicontinuous, then that sequence has a convergent subsequence. So, let me introduce what is uniformly bounded and equicontinuous sequence. So, uniformly bounded sequences and equicontinuous. Uniformly bounded and equicontinuous. Sequence of functions. So, my definition is, say definition 2, a sequence of functions say Fn defined on an interval AB is said to be uniformly bounded. A sequence of function Fn defined on AB is said to be uniformly bounded if there exists a positive constant, if there exists a constant, call it m greater than 0, such that Fn of x, the absolute value of Fn of x is less than or equal to m for all x in the interval AB and for all n is equal to 1, 2, 3, etc. So, there exists a constant m which is independent of n. So, uniformly there is a bound for each of the function in the sequence. Then we say that the sequence of function is uniformly bounded. An example of this, example say 2. So, consider a sequence of functions Fn defined by say Fnx is equal to sin nx, Fn is equal to sin nx, where x is varying in the interval 0 to 2 pi and n is equal to 1, 2, 3, etc. is a sequence of functions. So, as absolute value of Fnx, which is the absolute value of sin nx, which is less than or equal to 1 on the interval 0 2 pi, okay, and for all n is equal to 1, 2, 3. So, we conclude that Fnx is equal to sin nx is uniformly bounded. So, this is uniformly bounded. On the given interval 0 to 2 pi. Now, we define what is known as equicontinuity of a sequence of function. So, definition say 3, a sequence of functions a sequence of functions Fn defined on a sequence of function Fn defined on an interval AB, defined on an interval AB is said to be equicontinuous on the interval AB if so a sequence of functions Fn defined on an interval AB is said to be equicontinuous on the same interval AB. So is said to be equicontinuous on the interval AB if for every epsilon greater than 0 there exists a delta. That delta is a function of epsilon. For every epsilon greater than 0 there exists a delta. That delta depends on epsilon but is independent of n. So, it does not matter from which function n it is coming. So, independent of n such that the absolute value of Fnx minus Fny is less than epsilon whenever absolute value of x minus y is less than delta. See, a sequence of function Fn defined on an interval AB is said to be equicontinuous if for every epsilon greater than 0 there exists a delta. So, we should be able to find a delta which is independent of n, does not matter from which which function Fn it is coming. So, such that Fnx minus Fny is less than epsilon whenever x minus y is less than this delta. So, the equicontinuity is a continuity in the uniform sense for all n. So, note that the number delta is independent of the choice of function. From the sequence. So, theorem known as Arcela-Ascoli theorem, theorem number 2. So, it states that let Fn be a sequence of functions in the set of all continuous functions defined on the interval AB. So, let Fn be a sequence of functions in the space CAB. CAB is the space of all continuous functions defined on AB. and if Fn, the sequence Fn is uniformly bounded, if the sequence Fn is uniformly bounded and equicontinuous on the interval AB, then the conclusion of the theorem is, then there is a uniformly convergent subsequence, call it Fnk, for Fn. If Fn is a sequence which is which are functions from the space AB, and if Fn is a uniformly bounded and equicontinuous set of functions on AB, then there is a uniformly convergent subsequence Fnk for the original sequence Fn. So, this result is known as Arcela-Ascoli theorem, which we will be using for proving the excisions theorem for the initial value problem. For the proof, one may refer to any standard book on analysis, or it is also given in Coddington and Levinson. Refer Coddington and Levinson. Coddington and Levinson's book on theory of differential equations. Now we move on to next topic, which will be used in proving the uniqueness of solution of initial value problem, namely the Lipschitz continuity. So, Lipschitz continuity. So, Lipschitz continuity of functions. So, initially, for the sake of simplicity, we will define Lipschitz continuity for a one variable function. Okay. So, definition. So, this is definition 4 in this lecture. A function f from R to R, a real valued function from the real from the domain as a real space, is said to be Lipschitz, is said to be Lipschitz continuous, said to be Lipschitz continuous also is known as f satisfies a Lipschitz condition. Okay, we refer to this notion as Lipschitz continuity. A function f from R to R is said to be Lipschitz continuous on a subset say D, which is a subset of R, if there exists constant, call it alpha strictly positive, such that a function f from R to R is said to be Lipschitz continuous on a subset D of R if there exists a constant alpha greater than 0 such that the absolute value of f of x minus f of y is less than or equal to alpha times x minus y for all x y in the subset D of R. So, in this case, so we now call the constant alpha as the Lipschitz constant of f. In fact, if alpha is a number satisfying this inequality, then any number larger than that will also satisfy this inequality. We take alpha the least upper bound of all such alphas, and so that alpha we call as a Lipschitz constant. The least number which is the smallest number which is satisfying this inequality is known as a Lipschitz constant of f. And if in case D is the all real line, so we here assume the definition that D is a subset of R. In case D is all real line, then we say that f is Lipschitz globally. So, then f is globally Lipschitz continuous. Otherwise f is locally Lipschitz. So, if the condition is true, is satisfied in the whole space, then the Lipschitz continuity is a global Lipschitz continuity, or if it is restricted to a subset of the real line, then it is a local Lipschitz continuity. Now, we take a few examples showing the Lipschitz continuity. So, let us take examples. So, example call it 4. So, consider a function f from R to R defined by f of x is equal to 2x plus 3. So, this function f of x is equal to 2x plus 3, obviously this function is not a linear function. We check the Lipschitz continuity of this function. F of x minus f of y is 2x plus 3 minus 2y plus 3. So, if we take the absolute value, so this is less than or equal to 2 times or equal to 2 times x minus y. So, this implies that this is true for all x and y in R. So, f x is equal to 2x plus 3 is globally Lipschitz with the Lipschitz constant alpha is given by 2. Now consider another example. So example 5. So define or consider a function, f from R2 to R defined by f of x is equal to x square. F of x is equal to x square. So f of x is equal to x square. Now to check the Lipschitz continuity, f of x minus f of y, which is equal to x square minus y square, which is equal to x plus y into x minus y. So the absolute value of f of x minus f of y is equal to x plus y into x minus y. Now this quantity, consider this quantity, absolute value of x plus y. This is not a bounded quantity if x and y are allowed to vary in the entire real line. Okay. So but if x and y are varying in a bounded set, then this modulus absolute value of x plus y is a bounded quantity. So if x and y are varying in a bounded set, say x is less than or equal to a and y is less than or equal to b. Okay, in that case f of x minus f of y is less than or equal to, so this value x plus y could be alpha times x minus y, where alpha is a bound for x plus y, where x and y are bounded by these two constants. So therefore alpha is a finite quantity. So therefore fx is equal to x square is locally Lipschitz. So if this is locally Lipschitz, so if x and y are varying from, if for example if x is if f is defined from a set minus a to a to r, fx is equal to x square, then fx is equal to x square is Lipschitz, with alpha is equal to 2a, where x can take maximum value up to a, and x varies from minus a to a, and y is also varying from minus a to a. So, therefore, absolute value of x plus y that can take a maximum up to a plus a, that is 2a. So, therefore, the Lipschitz constant is 2a. So, therefore, f x is equal to x square is locally Lipschitz on a domain say D, which is set of all x such that x is less than or equal to a. With Lipschitz constant alpha is equal to 2a. Now, one can provide sufficient condition to ensure that a function is Lipschitz. See, sufficient condition to ensure that a function is Lipschitz sufficient condition to guarantee Lipschitz continuity. So, I state in the form of a theorem. So, theorem 3, suppose that f is a function from D, which is a subset of R, and mapping to R is differentiable on D, and the supremum of the bound of the derivative when x varies on D is say alpha, is a finite quantity, then the conclusion is then the function f is Lipschitz continuous on D with Lipschitz constant alpha, Lipschitz constant alpha. The proof is very simple, just by using the mean value theorem. By the mean value theorem, f of x minus f of y is equal to the derivative of the function evaluated at some point psi times x minus y, where psi is a point lies between x and y. So, therefore, this implies that the absolute value of f x minus f y, which is less than or equal to sup of f prime psi into x minus y. and this quantity is our alpha. By hypothesis, this is a this soup exists and is bounded by alpha. So, therefore, this is less than or equal to alpha times x minus y for all x y in the domain D. And if D happens to be the all real line, then the Lipschitz continuity we obtain is a global Lipschitz continuity. So, global Lipschitz continuity can also be given in terms of the bound of the derivative. If the derivative of a function is the slope of a function is bounded globally, then the function is Lipschitz continuous globally. If the slope is or the derivative is bounded on a bounded set, then the function is Lipschitz continuous on that bounded set. And we note that the condition in this theorem is just as sufficient. So, we note that condition in the theorem is just sufficient. But not necessary for Lipschitz continuity. So, that means we can produce example where a function is Lipschitz continuous, at the same time the conditions of the theorem is violated. So, example say 6. So, we take a function f x is equal to mod x, and f is defined from R to R. So, obviously f x minus f y is mod x minus mod y. If we take the absolute value f of x minus f of y, which is absolute value of mod x minus mod y. So, it can be shown easily that this is less than or equal to absolute value of x minus y for all x y in R. So, what does it say? So, this implies that f x is equal to mod x is Lipschitz continuous with the Lipschitz constant alpha as 1. However, f does not satisfy the condition of theorem 3. Theorem 3 we stated above. The reason is f is not differentiable at 0 to verify the condition stated in the theorem. If we take another example, so example 7. So, consider the function f x is equal to sin x. And to verify whether this function is Lipschitz or not, f x minus f y, which is sin x minus sin y, and if I want to take and I want to show if f is Lipschitz, then there exists a constant alpha such that is less than or equal to that constant alpha times absolute value of x minus y. So, how to show this? It is not that straightforward, provided if you use some trigonometric identities you may be able to, but if you just apply the theorem 3, the sufficient condition for Lipschitz continuity, that ensures that the function f x is equal to sin x is Lipschitz continuous. So, how? Because f prime x is cos x and it is bounded. So, cos x is bounded by 1 for all x. So, therefore, by theorem 3 there is a sufficient condition for Lipschitz continuity, implies f x is equal to sin x is Lipschitz continuous with the Lipschitz constant alpha is equal to 1. So, it is a very good test. If you just recall the function which we considered f x is equal to x square, the derivative is 2x, okay, f prime x is 2x, and 2x is not bounded globally, but whenever x is bounded 2x is bounded. So, f prime x is bounded so whenever x is bounded. So, in a bounded domain f x is equal to x square is Lipschitz, or that is locally Lipschitz. And if you look at the function f x is equal to sin x, f x is equal to sin x is globally Lipschitz, f x is equal to x square is not globally Lipschitz, okay, but it is locally Lipschitz. So, not globally Lipschitz. So, because of this, so this says that is locally Lipschitz. Now, we require this Lipschitz condition for functions of two variables that we will deal with in the next session. So, therefore, in this session we have analyzed the uniform convergence of a series of functions, and by using the Weierstrass M test we can make sure we can test whether a given series of function is convergent uniformly or not. And also we have defined what is equicontinuous function and uniformly bounded functions of a sequence of functions. And finally, we stated the Arzola-Ascoli theorem, which says that every uniformly bounded and equicontinuous function defined on a bounded interval a b has a convergent subsequence. We will deal with Lipschitz continuity for functions of two variables in the next session. Okay.